This is the Lunyee 3020 Nova desktop CNC. After my admittedly disappointing experience with a generic 3018, I was pretty stoked when Lunyee reached out telling me about the Nova, because this thing uses HGR15 linear rails and ball screws on all three axes, on top of an all-metal construction which should solve all the rigidity issues I was struggling with at the time. It also uses an 800-watt trim router as a spindle, except contrary to any random one you can grab off of Amazon, this one takes standard ER11 colloids instead of whatever proprietary junk this uses. It's powered by 60mm NEMA 17 stepper motors, though they are open loop, so that's likely the minimum needed to get enough torque, because this thing's supposed to eat wood for breakfast, mill aluminum for lunch, and PCBs at dinner. Now, I was sent this machine free of charge for the purpose of this review, but I'm reviewing it in accordance with my review policy, link in description, which means Lunyee is not getting to have any input on what I say about it, nor did they get to see the video before publishing. I did agree to a set of quote-unquote video requirements because those mostly matched up with what I was planning to do anyway, but as much as I genuinely want this CNC to do well in my testing, and obviously am not keen on raining on anyone's parade after they went to the effort of developing what looks like a promising new product, I am going to be candid about it when I consider something a shortcoming. In a day and age where the term review is regularly repurposed to mean unpaid product placements posted by influencers who don't necessarily know a lot about the thing they are reviewing in the first place, but feel compelled to say something positive about the expensive piece of equipment they just got sent, I feel like I need to properly disclose my motivations here. Now, seeing as my reviews are extraordinarily detailed and the last one ended up being nothing short of an hour long, I'm going to do things a bit differently this time and split it up into two parts. Today, we're going to unbox the machine and try it out doing a lot of milling to properly test it and see just how far we can push it. And the next video will be a full teardown and sort of quality assessment to find out exactly what makes this thing tick and what potentially could be improved on it. While I can probably give my preliminary 2 cents on it by the end of this video, I consider all these things important for prospective customers to know, so I highly recommend watching the second part, which should pop up somewhere here if you're watching from the future after I filmed and uploaded it, to know whether I can recommend buying it or not. With all that covered, let's get to unboxing. You get a little box of accessories, which includes a 1/4-inch end mill, some engraving bits, a spare collet, and replacement carbon brushes for the router. And this box was slightly broken. One of the bolts somehow punched a hole in it, but that's okay. There's also a power cable, some clamps for work holding, a paintbrush and steel ruler, zip ties, presumably for cable management, the user manual, which we'll take a closer look at later, some wrenches for the collet chuck, a basic Z-probe, and the USB A to B cable. Underneath we got the spindle clamp, which is an impressive chunk of machined and nicely anodized aluminum, the router spindle, which definitely looks a bit nicer than your average $65 Amazon trim router. Then there's the Z-axis assembly itself, which is also anodized and has a PCB carrying the limit switches and some connectors for the wiring on the back. And finally, there's only the machine itself left, which is too heavy to pull out of the box like that on the table, but tipping it over and dragging it out works pretty well. Overall, I'd say the packaging is impeccable, 10 out of 10, nothing should break. And here it is. My initial impression is, oh my gosh, what a freaking hunk of metal. It is such a different story from the generic 3018, which is partially made from plastic. Of course, this comparison is basically worthless since the Nova also costs like 3 times as much, and if we're supposed to mill aluminum, it better be heavy and rigid as heck. Which it honestly really feels like manhandling it like this. It's not like I cannot get some torsional deflection of the bed if I really try, but without having run detailed tests with a dial indicator, I'd say it's pretty good. But nothing is all sunshine and roses, so out of the box, my first nitpick would actually be the scratch in the bed mine came with. Obviously this is purely cosmetic and arguably doesn't matter if the whole thing is soon going to be scratched a whole lot worse, but next to the beautiful orange anodization of the frame, it seems a bit of a shame. What actually bothers me though is how the bed is anything but flat. If I put the ruler across here, you can see it rock back and forth quite ridiculously. This is because the bed is made up of two individual segments of 2100 extrusion, which they join in the middle. Judging from a quick Google search, actual 2200 extrusion basically doesn't exist or is extremely hard to come by, so short of getting a batch custom made, this probably made sense for them, although knowing that doesn't make the bed any flatter. That being said, it fortunately should be relatively easy to fix by shimming the extrusions where they mount on these sheet metal brackets, something we'll try in the teardown episode. And if you plan on using a spoilboard on there, it probably doesn't matter anyway. But let's finish assembling what little there is left to assemble. You mainly just have to screw on the Z-axis, which obviously needs to be aligned correctly perpendicular to the bed, something I'm only half-assing here because right now I'm not interested in perfect spindle tram. Then there's only the spindle clamp left, which has some alignment pins to help put it into the correct holes amidst the myriad of other available mounting patterns. This is arguably a double-edged sword because it'll prevent you from actually adjusting your spindle tram, so I'd say if you're skilled as a machinist, skip them to tram your spindle correctly, but any novice CNC user should probably put them in to avoid gross misalignments. The cable management mostly consists of plugging in the connectors and zip tying the trim router power cord to the umbilical, and that's it. Barely anything to assemble, which is appreciated. Not least because it's much less effort for me to film. Honestly, I keep finding myself impressed with how rigid the all-metal construction makes this thing feel. Again, it's not as if there is zero discernible deflection when I apply some decent force here. I can see it go up a few tenths of a millimeter with respect to the bed, so you are sooner or later going to hit some limits when machining metal, but the HGR15 rails really go a long way to making a solid machine, and in wood, I expect to be able to take some pretty big cuts on this thing without any issues at all. I'm also really glad they put a shroud over the Y-axis ball screw to stop chips and swerve falling on it, which is important to prevent since they do not have a wiper seal like linear rails do. But even still, I wish they would have done the same for the rails as well, just so we don't have to rely on that wiper seal, which is not foolproof, to prevent stuff from getting in there. So unless you plan to only run the machine with dust collection, I would highly recommend bending a piece of sheet metal or 3D printing something to attach to the frame and cover those rails up. Speaking of rails, out of the factory they're quite grimy with a bunch of crap sticking to them, and they aren't actually greased. There is something oily on them, but I'm pretty sure this is rust inhibitor and not lubricant. Actually, I take that back, I'm not sure. Upon closer inspection, the ball screws do have wiper seals and were actually greased, so it would make very little sense for them to not also have lubricated the rails. I don't know. Either way, you're probably safe running it for the first few hours without additional lubrication, after wiping off the grime, that is. It's always better to be safe than sorry though, and put some known good grease in there right away. Because talking about proper lubrication techniques would take me at least a few minutes here, when in actuality I have to get as many hours on this thing as I can if we want to see how it performs. I'm just quickly giving it some shots into the respective grease ports, and we're going to properly cover that step later in the teardown video, which should make a lot more sense anyway. Also, I noticed none of the screws on this thing were actually thread locked, which was probably to be expected, but is kind of questionable at best on a machine meant to cut aluminum, because the vibrations from that are almost guaranteed to make them come loose eventually. Again, I have a lot more to say about this than time right now, so let's kick that can down the road as well. I just have to mention it here for anyone who might not bother to watch part 2. Anyway, let's fire it up and see what it can do. Now, unfortunately, setting it up didn't go as smoothly as I expected. I plugged it into the computer and got the power cord hooked up, but it somehow didn't show up in the serial port drop-down of Universal G-Code Sender, even though the switch definitely was in the on position. So I went on to do some generic troubleshooting, power cycling, and trying different USB ports on the computer, figuring it might be a Linux-related port issue since that's what I run on this old laptop. No matter what I did though, it just wouldn't connect. In fact, it didn't even show up in my list of connected USB devices when I interrogated the terminal. For a sanity check, I decided to try the 3018 again real quick, and that one worked just fine. This really didn't make any sense, seeing as the Nova incorporates the exact same CH340G USB controller chip, so there really couldn't have been a driver issue or anything. In the end, I carried the heavy thing upstairs to try on my main PC, which still runs Windows, just to rule out it being a Linux-specific issue. Lo and behold, it didn't work there either. No matter which USB port I tried, I didn't get the ba-ding sound I should have when connecting a new device. Even checking the power supply, it seemed the board was getting 48 volts just fine. Only then did I realize, in a stroke of genius, that I hadn't tried disengaging the e-stop yet. Oh, it made a noise. There we go. Yeah. So they clearly went quite conservative on their accelerations as well. Let's try homing. Yeah, that's going to take a while. Yeah, that took an embarrassingly long time to figure out. But we're up and running. Just don't forget to disengage the e-stop. What a stupid mistake. In my defense, the setup section of the manual doesn't once mention checking the emergency button. However, it turns out they do say so in the common troubleshooting section. So joke's still on me for not reading the manual properly. On the flip side, we now know that the e-stop completely and physically kills power to the controller. Yeah, so they're doing the exact same thing I already previously noticed on the 3018, which is setting the accelerations to some incredibly conservative value. In this case, 20 millimeters per second squared. I wish I knew whether there's an actual reason for this other than companies being incredibly overcautious, but I just cannot stand the way it takes this long for it to get up to speed, even on travel moves. So I'm going to take the liberty and increase it 20-fold to 400, which should still be perfectly fine, but make things a lot snappier. And that's a lot better. I see no reason why it shouldn't be able to do these accelerations. It's not too much. As it turns out, there is a reason, albeit definitely not the one I expected. Basically, as soon as I crank up the speed settings, it reliably fails homing. Even though I spent quite a while fiddling around trying different values, I for some reason just couldn't get it to work at these higher speeds. And I think this is to do with the dissimilar limit switches they used on X, Y, and Z. As you can see, there's normal micro switches on X as well as Y, but on Z they use clicky push buttons instead. And in my understanding, this is causing issues with the debounce delay, which would need to be different for each type of switch, but Gerbil only lets me set a single value. I'll definitely have to dig a lot deeper than I can right now, but to be honest, I am a bit miffed because even though the cheap 3018 came with similar settings, I was at least able to crank them up just fine, whereas here it seems I'm stuck with 100 millimeters per second squared accelerations and a z-axis capped at 100 millimeters per minute, maximum speed for no physical reason at all. Just to clarify, anyone new to CNC watching this, please feel free to completely ignore everything I just said. You can totally use the machine just fine with the default settings out of the box. I'm merely concerned about the future upgradability here because sooner or later the settings it ships with will feel excruciatingly slow, especially on a machine like this which is physically capable of so much more. I will be running a speed demonstration here in a bit to show what I mean, and this will be particularly interesting for anyone interested in using this thing as a tool to like manufacture stuff for business rather than as a toy. Anyway, sorry for the tangent, we've got a first test cut to do. Because I can't really run this thing with dust collection for video reasons, and I already have them printed, I'm gonna go ahead and install these rail guards straight away. They just stick on using double-sided tape, and I'll have them available on printables via a link in the description for anyone interested. First off, we have some demo files on the included USB drive. Let's run them all. It's worth noting here that I reverted all the machine settings back to the stock profile it came with, just so you get as authentic an experience here as possible. Nothing sped up in post, nothing cut out, just switching back and forth between camera angles. I'm using one of the 1/8" carbide end mills that came with the machine, and the material here is 4mm poplar plywood. The feed rate with this pre-sliced G-code file is just a smidge over 1000 millimeters per minute, and I'm running the spindle at a theoretically correct 8400 RPM, give or take. And as you can see, this is really not too bad. It's eating through that wood like butter at a rate no less than 10 times what I was able to do on the dinky 3018. So to better explain my slight irritation just earlier, let me tell you that for an easy part like this, a machine built as sturdily as the 3020 Nova should be perfectly capable of going no less than twice as fast without noticeable loss in quality, literally cutting machining times in half. Keep that in mind for later. That being said, yes, if you don't happen to run a business where increased CNC time is basically money left on the table, or are incredibly impatient like me, then the Nova is probably perfectly fast enough. The end result looks pretty good, save for all the burrs, which I can assure you are more of an issue with the wood species in general and the router RPM I chose than the machine itself. they can be sanded off relatively easily, and the cut quality is honestly just as good, if not better, than what I usually get on the table saw. It is admittedly an easy test, but thumbs up nonetheless. Next up, we have a goofy smiley face, and this is an engraving, so I'm using painted MDF as a material here for better contrast, and one of the more obtuse engraving bits for a wide cut. I really should have cranked up the spindle RPM a lot here to make up for the smaller effective diameter, but I forgot, so the result turned out a little fuzzier than usual. It's still pretty good though. The fuzz can easily be taken off with a fine sandpaper, and yeah, it's good. I have nothing to remark on. For the next engraving, I wanted to try plexiglass, and this time I actually remembered to turn up the spindle, but just like incorrectly focusing my camera, that proved to be a very bad idea. I think the problem is that this V engraving bit doesn't really have much to show in terms of a cutting edge. It's basically just got this pyramid type point, which inherently does more scraping than actual cutting. The one thing plastic really doesn't like. While running it again at a lower RPM did produce an actual result, it's still not very nice and looks a bit melty, so let's try again using this pointy single flute bit instead. Unfortunately, that didn't change much, and just a few seconds into the cut, I was again getting a little blob of molten plastic sticking to the tip of the cutter, something that even dropping the RPM didn't fix. I ended up running the same cut a few more times to clean things up, and it honestly took me way longer than I care to admit to realize what the problem was. Chip evacuation. The 500-ish millimeter per minute feed rate and depth of cut of 0.3 millimeters may just be pushing things a bit too far in plastic with a super pointy bit like that, where the chips don't have the space to go anywhere in the narrow groove it cuts. Because I was trying to salvage this piece, I kept rerunning the cut with the Z height lowered by 0.05 millimeters each time to take off only the tiniest amount of material, and that worked just fine. I guess there's some truth to it when they say you should never bite off more than you can chew. Oh yeah, that looks a million times better. Once I get rid of these burrs, which can apparently just be rubbed off like that, it's a nice and deep cut. Bottom line, a bigger, more powerful machine does not necessarily speed up the engraving process, especially not when you don't know what you're doing. Unlike a 3D printer, where most of the time these days you just push a button and out pops the finished part, CNC requires actual skill and knowledge from the operator to achieve good results, which is why reviews, including this one here, are inherently quite subjective when showing the machine's capabilities. Now, for this last engraving, we have the Lunyee logo, which I'm pretty sure was meant to be done in aluminum based on the feed rates and depth of cut I can see in the pre-sliced G-code file, so let's do exactly that. I just ran some tests here off camera to double check those feeds and speeds so I don't ruin that piece too on the first attempt, and while it engraves fine, it seems to raise a terrible burr on the edges of the groove, something that didn't change at all regardless of the different chip loads I tried. Which ultimately reminded me of the fact that when I tested the 3018, the little single flute V engraver bits that came with the machine were extremely inconsistent in grind and kind of hit or miss in terms of how well they actually cut stuff. Looking at the one I've been using so far up close, I can't see anything obviously wrong with it, but it does have a bit of a strange flat right about here. In theory, that side shouldn't be doing any cutting anyway, but it always depends on how concentric the actual tip is with the shank and how much run out the spindle adds. So I popped in one of the ones I got with the 3018 just to try, and sure enough, on those leftmost two cuts I did with that one, you can clearly see it leaves less of a burr on top of cutting a narrower groove. The one I was using with the plexiglass definitely plows through the material more than cutting it, which almost certainly also contributed a lot to the plastic melting. Now the Nova only comes with two of these things, so let's try the second one and see if it's any better. Okay, it's about on par with the other one. I'm not really sure right now how to get it perfect, but depending on the alloy, aluminum is bound to be a bit difficult in this scenario due to how gummy it is. We are just pushing a glorified toothpick through it after all, so you might very possibly need an actual good quality V-carving bit to really get decent results. Off the cuff like that, I really don't know what the problem might be. It could be the quality of the engraving bit, sure. It could also be a particularly gummy alloy of aluminum. It could be bad chip evacuation. I almost certainly am using wrong feeds and speeds due to the pre-sliced G-code file, and I might need coolant to get it to actually cut material rather than just push it out of the way. Plus, this engraving bit is not DLC coated, which makes it kind of unsuitable for aluminum in the first place. All that and any of those might be leading to the same problem we already had with the plexiglass, material clogging up the tip of the engraver, preventing it from cutting anything altogether. Long story short, that's what I meant by CNC requires skill, something I do not in the slightest pretend to have anywhere near enough of. I will figure it out with enough trial and error off camera when I can actually concentrate, but right now we're just messing around anyway. If there's one thing I want you to take away from this video, it's that getting good results in wood, while very important for a machine and review like this, doesn't really say a lot about anything at all, because as a material, wood really mostly eschews the signs of machining. Pick a feed rate, crank up your spindle RPM almost however high you like, and you will get, more often than not, a pretty good result. Now, getting an accurate and consistent carving depth in this visibly warped piece of aluminum is where the Z probe comes in, but unfortunately mine here doesn't seem to be working the way it should. If I measure the thickness like the manual tells me to and get it plugged in and set up to probe with the alligator clip clamped on the end mill, and then enter the measured height in the probe menu in Universal G-code Center and hit probe, it immediately goes into an alarm state throwing an error. Specifically, the error message mentions the probe not being in the expected initial state, which is weird, but in the DRO section here it usually shows any activated limit switches, so if I click this one here, you can see the red X appearing. Except, it's showing probe the entire time, which it shouldn't because it isn't anywhere close to touching. Moreover, if I touch the probe base to the end mill, which is really the way it's meant to work, for some reason, nothing happens. But if I remove the alligator clip from the end mill, suddenly the indicator goes away. If I put it back on, it reappears. This has me pretty sure they got the polarity of this plug reversed, precisely because it doesn't work the way it's supposed to, despite the bare clip on the probe triggering just as intended. So let's swap the polarity here and see if I'm right. And yep, wouldn't you know it. The reason for this is that the probe operates between a signal line and circuit ground. But because the controller board is properly grounded to the chassis like it should, and the entire machine happens to be made of metal, there's actually a current path all the way from the controller ground to the end mill. So when you clip the signal line to the end mill, you're inadvertently completing the very circuit the probe was meant to momentarily close, which unsurprisingly throws an error. Alright, save for the birds, it looks like it turned out pretty well. This is actually the first time I've ever used auto leveling on a CNC, and I have to say, it was pretty easy. Okay, that might not have been the smartest way to go about post-processing since it mostly just filled everything back up with crap, but overall it still looks pretty good. Last but not least, we have a relief carving to try, which is great because I've never done one of those either. So much for my level of expertise going into this. The whole artsy engraving shtick is just not really my wheelhouse. But fortunately, I'm going to use wood for this, not aluminum. More specifically, Hollywood. No, not that kind of Hollywood, the tree one. But first I need to face mill it a bit to true up the surface since it's very warped from drying. Yes, it's homemade wood, so to speak, just a thick branch I cut off the tree in the garden, resawed, and left to dry. I do that from time to time since there's lots of nice hardwood growing around here. I just never know what to do with it in the end since, again, I'm not really into art projects and stuff. Fortunately, face milling is a piece of cake for the Nova, and we're left with a nice flat surface in no time. Given my lack of dust collection, that made one heck of a mess, but oh my gosh, the result. It really goes through hardwood like butter. I could have gone much more aggressive than that without running into issues. Oh my gosh, that came out absolutely gorgeous. This is insane. It did take nothing short of 5 hours and 20 minutes to complete, but I guess we can try speeding things up a little in a bit. Let me just cut around this while I have it in the machine and then we can take a closer look. Okay, aside from some very unfortunate cracks in the wood, which I didn't see from the outside, this thing came out practically perfect. The detail here is nothing short of mind-boggling. It's so small, I'm actually having a hard time even filming this, so let me show you some B-roll of it. It just looks really good. On camera here, it's actually quite a bit easier to make out the subject amidst all the swirls and textures, I think because of the contrast. In real life, it took me longer than I care to admit to see the dragon, even though I knew I was looking at one, due to how easy it seems to be to get lost in the 3D-ishness. I don't know, maybe I'm just no good at appreciating the art of sculptures and relief carvings. I also took a bunch of macro pictures, and these are focus stacked and sharpened so you can see more detail in them than you could make out with the naked eye. So this is at the scale at which we can see small imperfections like the scan lines and some light fluff in certain areas. These are tiny wood fibers that weren't properly cut by the V-bit and are still stuck to the model. But like I said, they're so small you wouldn't notice them unless you started scrutinizing the thing with a magnifying glass. I legit only noticed them on the photos here while editing. So yeah, as far as what it actually looks like, this one here probably comes closest. Now, this is all very nice, and from what I can tell so far, the Nova is perfect for serious woodworking projects, but as we all know, the difference between science and screwing around is writing it down. So joke's on you if you thought any of what I did until now counts as testing. Let's get our ass in gear and do some real milling. The first step is cranking up those accelerations and speeds to some more sensible values, because with the Z-axis limited to 100 millimeters per minute, how am I supposed to do plunge cuts at 200 millimeters per minute? Besides, I don't think wanting the Z-axis to move at a little bit more than this snail's pace is asking too much. Of course, this does break homing again, so I'm just gonna disable it. For what it's worth, homing in my experience isn't actually even that useful unless you've got the machine set up to produce multiple of the same part over and over again or something, since most of the time you just use local coordinate systems anyway. So I have not actually even been homing the machine in all the messing around so far, and can safely say I benefit more from the speed boost than retaining homing ability. The Lunyee website also states a maximum speed of 5,000 millimeters per minute, which is currently not at all implemented on the software side, so let's crank X and Y up as well in the spirit of, I paid for all that speed so I want to use it! That's so much better. We're zooming. Wee, 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 wee. Of course, with great power comes great responsibility, so be careful which button you press. I seriously hope that's the reason Lunyee decided to cap the Z-axis at those ridiculous 100 millimeters per minute, because if it goes faster, you don't necessarily have time to hit the E-stop before disaster strikes. That's definitely why I didn't go beyond 1000 millimeters per minute just now, although I guess something could be said about stepper motor torque drop-off and skipping steps at higher speeds, so maybe I should have gone faster to counterintuitively make it safer. Anyway, to start with, I want to install and level a spoilboard. This is made a tad annoying by the warped bed, so I'm shimming the edges to make it lie a bit flatter. I could just brute force tighten it down and rely on the spoilboard to either straighten the bed or assume the same curve, but that would put it under tension, which might make stuff shift around when I weaken it by removing material. As expected, facing is a breeze with a 6mm carbide end mill. I'm doing 2000 millimeters per minute here at a depth of cut of somewhere between 0.5 and 1mm and 60% step over, though this is still taking it very conservatively at less than half the theoretical chip load, and science says I should be able to run it at full tilt 5000 millimeters per minute without even cranking up the RPM all that much. I'm also using a bit of dust collection here because I'm already tired of getting sawdust everywhere. This took just over 8 minutes to complete, leaving what can only be described as an impeccable surface. First, we're going to be cutting this spur gear out of a bunch of materials, and I'm starting off with poplar plywood, and because I'm pretty confident the machine can take it, the depth of cut here is no less than 5 millimeters. I'm also back to the small 1/8 inch end mill that came with the machine, and we're again going at 2000 millimeters a minute, which looks ludicrous on a part this small, but still only corresponds to about 2/3 of the calculated chip load. And I mean, look at it go! Okay, that was epic, not gonna lie. It took all of 53 seconds to cut out this gear. Let's see what it's like. So it didn't cut all the way through, which, measuring the thickness in hindsight, is not surprising since the plywood is a little bit oversized. The top edge is quite frayed obviously, but that's totally to be expected with how fast I went. Nonetheless, the corners are not too wrecked. There's only a few bigger splinters missing here and there, and the surface quality of the cut is still pretty good. Now, I can see a slight ridge between the first and second pass, which is also not surprising given the cutting forces involved can be quite substantial at large depths of cut. So a small end mill like this is absolutely going to deflect a bit, and you wouldn't normally cut something out at these speeds without afterward doing a spring pass to clean up the edge and take off that last 1/10 of a millimeter. But you can do it if for some reason you need to, and that's what I'm here for to demonstrate. Of course, if I can cut through 10mm plywood in 2 passes, I can absolutely take 4mm plywood in a single pass, which is pretty rad. I'm taking it a bit slower at half the feed rate this time to hopefully reduce tear out a bit, since poplar is really quite bad in that regard. Oopsie. Those tabs clearly were not sufficient for holding it in, but yeah, cut quality is noticeably better this time, although the tear out didn't really improve. I'd have to go way slower still, which is just an inherent problem with wood in my experience, especially soft woods. Moving on to a deceivingly simple material, common spruce. This stuff absolutely annihilated the little 3018 due to the strong grain and stringy fibers wreaking havoc on any machine lacking rigidity. Fortunately, the Nova still shreds through it like a literal wood chipper, though you can tell from the pitch of the router sometimes that it's loaded down a little heavier than before. I also got a little more fancy with my tool paths, so we're now hogging out the majority of the material at a decent 1000 millimeters per minute, and then going back in for a full depth finishing pass at a measly 200 to clean it up. Of course, that fanciness came at a hefty cost in machining time because now we're up to 5 minutes for that same gear. Still not bad, but was it worth it? Well, looks like my finishing pass was a little too slow after all. We clearly went beyond burnishing there and actually discolored the wood. However, the surface quality is pretty excellent now. I would even go as far as to say you are not going to achieve any better without sanding. The bottom edge, which sat pressed up against the spoilboard, is basically perfect. Only the top has a bunch of tear out again, but ultimately you're never going to entirely get rid of this in any reasonable way. Easiest would probably be to just run a chamfering operation to clean up the burrs. Again, with CNC, there's a plethora of variables affecting surface quality and end result, so getting definitive and objective answers to what a machine is actually capable of is nigh impossible. This is now 8mm beech plywood in 2 passes, and I changed my strategy for the finishing operations, so we're now running at the same 1000 millimeters per minute, but taking many passes at a very low step down of 1mm. The goal here is really just to reduce cutting forces as much as possible, something my previous attempt with full engagement might not actually have achieved. And yes, I am indeed the kind of person to run a spoilboard on top of my spoilboard because I don't want to be resurfacing it all the time. Like any good scientist, we have to change several variables at a time so we can get nice results by chance and then not know how to reproduce them. This is the least amount of tear out yet, and I suspect we primarily have the different species of wood to thank for it, although the new toolpath probably helped as well. I mean, the surface quality is pretty much perfect. although I can see a slight stair-stepping effect, which likely means we're reaching the limits of rigidity of at the very least this 1/8 inch end mill, which would not be surprising. This is the hardest wood I'm testing on today, and it's pretty high up there in terms of toughness. On the other hand, this so far also took the longest to machine at almost 7.5 minutes. After that, it's quite clear how MDF is a piece of cake by comparison, so much so in fact that I didn't bother with a spring pass. I don't think it's something you would normally do unless you actually need the accuracy, since it just makes setting up the tool path take twice as long. This one did not cut all the way through either, and once again, it's not my fault, it's the stupid wood being completely out of spec. Interestingly, this is easily the least amount of tear out we got so far, and if I had done a finishing pass, it might have been even better. Of course I didn't, so we still get the same line between passes, although, like with the other gears, I cannot really feel a ridge or anything, it's more just a visual imperfection. This is HDF, and for reasons I'll get back to, I'm handling it with kid gloves here at only 500 millimeters per minute. To keep my chip load halfway reasonable, I also turned down the spindle, but even the first plunge showed this was a massive mistake, so I quickly turned it up again a notch, and another, which also didn't get the tear out under control. I was also very surprised to hear, for the first time on this machine, some slight chatter on the deeper cuts. Nothing too serious though, so let's just keep it in mind and blame it on the end mill or my work holding for the time being. This particular type of HDF is some very strange stuff. It's extremely dense, as the name implies, but it also contains little to no binders, so the edges absolutely love becoming fuzzy at the best of times, even on a simple bandsaw cut. Hence, I went into this knowing I would get a lot of tear out, which I clearly am. I'm also doing a finishing pass here again at a 1mm step down, because I just felt it would be necessary. That not only ended up very fluffy, made a ginormous mess of the place, but also took an absolute eternity at 16 minutes. Nevertheless, if we manage to look past the gnarly tear out situation at the top, the cut quality is pretty excellent. It looks a little bit burnished, which quickly happens with this stuff due to the density, and the step down from the finishing pass is clearly visible again, but overall, it's pretty good. I might even be able to go faster if I reduce my depth of cut to keep cutting forces low. And interestingly, this HDF really also kind of marks a watershed in the materials I'm testing here, because like I said, wood is basically cheating. Easy mode enabled. What I've been doing so far, like running at 2/3 of the chip load to begin with, and then additionally having the feed rate, would just be asking for trouble in plastics or metal. Too much rubbing and plastic's gonna melt, and aluminum loves galling, which can ruin your tooling in a heartbeat. So unfortunately, we gotta play by the rules now, or at least a bit more than we did till now. Who makes those rules if we don't get to do it ourselves? Science does. And there is a staggering amount of it involved in machining. I'm actually going to link this excellent article explaining everything in the video description, but for now, suffice to say, we need to know the spindle RPM in order to be able to crunch the numbers. This standalone router spindle, however, is not software controlled by the computer. It only has a speed control dial I can manually set to anywhere between 1 and 6 mystery units of RPM. So we need to figure out what exact RPM each number on the dial corresponds to, and the easiest way to do this is to stick a piece of paper tape with a retro-reflective marker on it to the collet chuck and simply measure the speed using one of those cheap optical tachometers. Of course, I already did all that earlier before starting testing, which is how you got all those infographic overlays on screen, so I'm now doing a dramatic reenactment uniquely for your viewing pleasure. Now, like with many cheap routers relying on generic brushed motors, there are speed ranges where you get more vibration from resonance due to the rotor not being entirely perfectly balanced, and my unit here really starts to make such an awful noise at the level 6 full speed position that I will avoid using that speed range altogether. But yeah, like I said, this is fairly common with cheap power tools in my experience, so I would not classify it as an issue with the 3020 Nova. I mapped out all the speeds in a note here, and interestingly, they're not only all very close to a nice and even RPM value, but also step up in increments of almost exactly 2,500 RPM each time, all the way up to speed setting 5, where it falls apart, and the difference drops to only 1,500. That tells me pretty much with certainty that this router is electronically speed regulated internally, which is a huge plus since it tries to maintain a constant RPM regardless of how much it's loaded down. I'm glad Lunyee did that because they could have just stuck in any generic unregulated router and you wouldn't tell the difference from a few pictures, even though the regulated one is far superior, if not indispensable for machining purposes. But I digress. We wanted to try plexiglass next, and for this thin stuff, I'm switching to the blue tape and super glue work holding technique, except I only have yellow painter's tape because the blue one is unreasonably expensive for some reason. Since we now know the RPMs we have available on the spindle, we can just enter one into a feed rate calculator along with some other cutting parameters, and it'll spit out a feed rate we can go at. Of course, I'm going to paste this lookup table in the video description so you can just refer to that instead of having to measure everything yourself. This online calculator, by the way, is developed by none other than patron Cause, so I'm going to unashamedly shill it here of my own free will because it really is quite convenient. The link will also be in the description, so you can just bookmark it in a browser or even install it as a web app, which has worked great for me on Windows as well as Linux. Now, as far as the acrylic is concerned, it's actually way more challenging than I expected. The sound it made was less than confidence-inspiring, and chip evacuation instantly seemed like a problem, with everything sort of staying inside the slot, so I got scared and paused it to get out the shop vac again, which would hopefully help a bit with cooling as well. And all of this here was after I already did a brief test off camera and discovered that climb cutting seems to be a very bad idea. It literally fuses the swarf to the workpiece again, so I was very cautious to only use conventional milling when generating the tool path for this gear. And yes, there is a full depth finishing pass to clean things up. Altogether, it came out pretty nice though, I would say. All the shavings come right off, leaving an almost perfect cut with very little burr. Now, I can see a slight ripple and an actual ridge from the step down in some places, which really shouldn't be since we had a finishing pass, but I suspect my work holding might have failed, allowing it to shift away from the cutter. And I'm definitely getting deflection and chatter thanks to the significant end mill stick out. This acrylic is noticeably harder than wood. And as if that didn't melt easily enough, what about PLA? This is recycled 3D printing waste. I just melted it into a 5mm sheet. Let's cut a gear out of that. And we are going fast, at 3,200 millimeters per minute to be exact, because I heard with plastic you want to go at a brisk pace to prevent it from melting since the chips take the heat out of the cut. But unfortunately, that alone was not enough here, because they also have to go somewhere, and even the shop vac sloppily following the cutter didn't manage to evacuate them all. So strings of plastic got tangled on the end mill, and I had to momentarily pause streaming to manually remove them. Yeah, not ideal. Nevertheless, I plowed on trying to save the piece, but alas, unsurprisingly, it happened again. Except this time I couldn't pause it in a travel move, so I had to interrupt the job and run it from the beginning again. Honestly, I might have been a little too ambitious here. Maybe you just cannot cut that fast without at least a dust shoe for decent dust extraction or an air blast setup to blow chips away. It probably would have worked with different settings, but quite frankly, you'll have to forgive me for grasping at straws here since I really have no experience machining anything other than wood. And yeah, going slower is usually the easy way out, but we're trying to test this machine, so like, what would even be the point? Well, that went over like a lead balloon. We're not even going to evaluate this one since it was clearly a failure on my part. It looks pretty terrible. I'll have to redeem myself, obviously, but for now I'm out of PLA sheets big enough because this stuff is kind of time consuming to make. So let's move on. The 3020 Nova is marketed as being capable of some serious small-ish scale aluminum milling, and so far I have little reason to doubt that. So let's cut an aluminum gear. Now this is where the cheap 1/8 inch carbide end mills that are supplied with the machine definitely don't cut it anymore, pun intended. So I acquired some better quality DLC coated ones in advance, knowing I'd need them. The DLC is practically requisite for aluminum milling because it prevents galling, and it apparently makes them this nice iridescent rainbow color, which is usually how you can tell. I also bought a bunch of aluminum scraps, but unfortunately not a single one of them is big enough to fit my test gear onto, so we're gonna have to make do with 16 gauge aluminum sheet. Mystery alloy salvaged from an old computer monitor. So with the end mill chucked such that I have as little stick out as possible and the workpiece held down by screws as well as the blue tape method, we're off. Because I'm completely new to machining aluminum and only have this single 3mm DLC end mill, which I therefore absolutely can't afford to break lest I upend some later tests, I opted for some pretty conservative feeds and speeds for once. So we're running 900mm per minute at 16,000 RPM with a depth of cut of only 0.5mm, and it just cuts beautifully. Like butter even. It's especially worth noting that what I'm doing here is not exactly ideal because I'm just straight cutting it out using a simple slotting operation like you would a piece of wood, whereas normally, in my understanding, when machining metal, you'd use something like adaptive clearing to ensure consistent tool engagement and allow the cutter to cool down again, which it cannot do in this case where I'm continuously cutting. But it still went just fine. I probably wouldn't risk it on heavier cuts or thicker stock though. Oh my gosh, I don't think I could have asked for this to go any better. This is literally perfect. Barely any burr, nice and clean edge, and I should be able to go a lot more aggressively before the machine starts breaking a sweat. Wow, this is crazy. Arguably the best result yet, not to mention easier than preventing the plastic from melting. I literally just plugged the number from the feed rate calculator straight into my CAM software, and that was it. It did take 4 minutes to complete, which I'm not crazy about, but we're gonna see about speeding things up in a bit when I get more comfortable with aluminum and less worried about breaking my only 3mm end mill. Seeing how smoothly that went, what else could I try? That's right, we're doing mild steel. I'm not kidding! Aluminum is very nice and all, but what if I need my gear to be more wear resistant? Once again, we're doing this on a piece of thin sheet stock because I unfortunately don't happen to have big scraps of 5mm steel plate kicking around, so sheet metal is about the best I can do for large parts like this. Now, there is apparently a rule of thumb saying you can't really machine something harder than what the machine itself is made out of because it just won't be rigid enough, so chatter really becomes an issue then. But I don't care. Imagine I really need this gear out of steel right this instant, and I'm willing to abuse my CNC just a little bit to get it. I think that's a situation any CNC owner might potentially find themselves in at some point. Of course, I was planning on testing this all along, so I conveniently also have matching end mills with an all-Tyson coating appropriate for ferrous metals. Let's do a simple test cut first to see how things go and make sure this is even possible at all. Okay, nothing broke. So far so good, I guess. Let's try another one. That definitely bogged the spindle down for a second before it adjusted to the required torque. Yeah, yeah, not too bad. There seems to be a little bit of chatter at this higher depth of cut, but my work holding on top of a stack of wood here is arguably atrocious for metal machining. It's like if I had mounted the MDF on a sheet of styrofoam earlier, effectively completely killing any rigidity the machine may have had. But yeah, I just want to surface this roughly cut off tab so I can try out a consistent depth of cut. That went surprisingly well despite my questionable work holding. Looks pretty flat and shiny to me, that does. Admittedly, I thought I was being conservative with a depth of cut of only 0.2 millimeters for a width of cut of 0.4, but seeing as the spindle had some trouble delivering that kind of torque, and I'm already operating at more or less the high end of RPM you'd usually mill steel at, unless you want to burn out your end mill or something, that's probably about the best we'll get, especially since plunging into the material to carve out a pocket or hole is going to put a lot more stress on the frame, not least because it engages the full width of cut. That, I believe, is definitely going to push the rigidity of this machine to its limit. After all, it's not a bridge board and it was never designed to replace one, so we shouldn't expect it to. So let's try the full width of cut, but with a depth of cut lowered to only 0.1 millimeters because I'm a bit worried. I'm also going to put some IPA on there for lubrication and cooling, although I'm told it won't do anything. Actually, editing Benjamin here, did you notice something? Rewatch this clip. Did you see how the spindle sort of gets pushed to the right the second it enters the cut? And then mostly springs back afterward? Yeah, that's not supposed to happen, nor is it entirely my fault for abusing the machine. Just keep that in mind for now. Anyway, back to the video. You know what? That seems to be working reasonably well. Let's go down another 0.1 millimeter. And another. The feed rate here is now down to 320 millimeters per minute, which I guess is par for the course with steel milling, so I'm for once going to stop complaining about it being too slow. The end mill also doesn't seem to be getting too hot, nor does it look wrecked quite yet. Fortunately, I'm sure I'll manage to destroy it eventually. We're down to 0.5 millimeters now, and it does sound like I'm getting some issues with chips being recut, which is absolutely not surprising in a slotting operation like this without any chip evacuation. Yeah, that's definitely showing signs of the machine not quite being up to the task. The bottom surface is not exactly smooth, and while one of the side walls is sort of okay, if you can even see it on camera here, the other one is quite rough with lots of chips mashed into it. Let's try some better work holding, and if that doesn't improve things, blow off the gear. I don't want to torture the machine too much here because we'll still need it. That ain't going anywhere. Alright, let's machine a hole. I'm again using a little bit of IPA for cooling in addition to having the vacuum cleaner running because this first plunge really kind of freaks me out. The end mill just has to get in somehow first. Everything after that I can easily do with a low step over to reduce cutting forces. But apparently I needn't have been so worried because it went in just fine. The advantage of making a hole is that I can just pour in some IPA and not have it instantly disappear. So even if it doesn't help much with lubrication, it's still going to do at least some cooling at this small scale because it just evaporates, taking the heat out of the metal. It's also worth noting just how much better the machine sounded with this more rigid work holding technique. Here it is with the shop vac turned off. Yeah, it's pretty good. I really couldn't hear much chatter at all. And it was at about this point, 3/4 of the way through the job, that I realized what an absolutely horrific idea it was to use isopropyl alcohol in addition to the vacuum cleaner for chip evacuation. because any of it, including its fumes that gets vacuumed up, passes straight through the motor with its continuous open arc discharge from the carbon brushes. Yeah. Thank God the concentration was low, or else you might not have gotten to see this video. Wow, that was nerve-wracking. The result, however, is actually pretty dang good. It's basically a perfectly usable edge, and I don't even see any of those lines from the step down. Actually, let me show you some pictures here because this shiny metal stuff is so difficult to keep in focus with video, especially at this scale. So here it is. As you can see, it's pretty much excellent, save for the little bit of cloudiness and horizontal streaks toward the bottom. This is actually aluminum contamination from cutting into the sheet underneath in order to go all the way through. So the aluminum got dragged up and rubbed into the surface of the steel, which it cold welded to. This was definitely a bad idea. I should have used the steel spoil piece instead, because now my end mill also looks like this with its coating presumably partially ruined. Anyway, the other side of the hole looks a bit worse for wear with a couple of extra dings which I'm relatively certain were caused by chips being sucked in and recut. But yeah, overall, pretty good I'd say. If you're in a pinch and you know what you're doing, the 3020 Nova can indeed mill steel on a small scale, even if it might not be the best idea. And that is largely thanks to the HGR15 linear rails on all axes. On most machines this size with a floating rod rail system, I'm pretty sure you don't even need to try. It's not going to be rigid enough. So, am I going to risk trying the gear? No, it's too sketchy. I don't feel qualified yet to safely test this. I'm not sure how I would even mount this floppy piece of sheet steel to the bed rigidly enough, though it's definitely something worth revisiting at some point in the future. I'm also having a little problem, unfortunately. As you probably noticed, the video runtime already surpassed 1 hour, which is no less than twice as long as I planned for it to be. But somehow I've still only just completed the very first stage of the very comprehensive testing protocol I put together. I'm not sure how I thought I would ever be able to machine like 34 test pieces when many machining channels spend an entire half-hour video making just a single part. So I'm afraid we'll have to postpone all the other tests and do them in the next video. Otherwise, this one here might end up 3 hours long and coming out around Christmas. Classic case of me biting off way more than I can chew, I guess. So let's just tie up some loose ends here, have fun with the machine for a second, and conclude with my current thoughts on the Lunyee 3020 Nova. Yes, carving this tiny part out of the center of that big piece of stock was a kind of wasteful use of resources. However, there's some cracks in the end grain that I didn't know how far they penetrated. But all in all, it came out quite well, I think. I kind of wish it were a little brighter, but I just chucked in a random jewel thief I had kicking around, and it would have to be optimized for current to properly drive 3 parallel LEDs. Anyway, let's get down to brass tacks and talk about the good and the bad I've noticed so far playing with this machine. Starting with the pros, first of all, it's obviously nice and rigid thanks to the linear rails on all axes and the all-metal construction. No question about it. Consider me a fan. In my opinion, all CNCs should be built like this. Hardly worth bothering with anything else in the first place. It's not like the floating rod arrangement you'll find on many other machines, including the Carvera Air, was ever a good idea from an engineering standpoint. Ergo, as a direct result of this rigidity, the machining capabilities here are pretty dang promising as well. Basically, whatever a palm router like this can handle in terms of torque, you should be able to throw at this machine. At least when it comes to raw, brute force material removal. The caveat here is accuracy, because it inherently drops as you take bigger, more aggressive cuts, even when your frame can ostensibly handle it, since rigidity is just never absolute. It's a shame I didn't get around to doing the maximum material removal rate test anymore today, but I promise we'll get to it next time. As for the overall quality of the machine and its components, at a first glance like this, without having literally scrutinized everything with a dial indicator, it honestly looks pretty good to me. Nothing to really complain about. Granted, it is import quality, you're not getting brand name rails here or anything, but things definitely look adequate quality for the price point to me. Same goes for the spindle. I have not measured the runout yet, but from everything I've done so far, I have zero reason to believe it would be any worse than the 0.05 millimeters or less you usually get from a woodworking router like this. Speaking of the router spindle, I really like that it's RPM controlled, and especially the ER11 compatible collet chuck, since that allows me to just reuse the collets I've already got. I didn't know CNC-oriented trim routers were even a thing, but they apparently are, although quite rare still, unfortunately. In fact, I can only find 2 in total, this one from Carbide 3D and a more similar one from Genmitsu. However, Lunyee does not seem to be selling this specific one separately, despite offering a whole bunch of parts including actual water-cooled spindle motors for upgrade. In any case, it's nice to see one like this bundled with the Nova, since for any machine that comes without a router pre-supplied, you'd have to go out of your way to buy one specifically with that feature. I also appreciate that they put some effort into cable management. More often than not these days, cable management is more or less an afterthought even on fairly serious machines whenever they're targeted at tech enthusiasts and DIYers, because, well, it's easier to just let the customer finish the job, right? But yeah, Lunyee definitely at least made an effort here, even if it's not quite perfect. Most of the cables going to the stepper motors and limit switches are neatly run inside the frame, but there is this stray cable here on the back going from the PSU to the controller box, even though it ostensibly could have just gone straight across between the two instead of awkwardly looping around the back like this. On the flip side, the cables for the stepper motors seem to be rubber insulated, which is actually the correct type to use in a more industrial environment where they might come into contact with oil and grease. And now for my absolute favorite thing about the 3020 Nova, which might even seem a bit silly. It makes no noise. I'm not kidding! Of course, if you fire up the router, it makes one heck of a racket. In fact, you kind of have to wear hearing protection around these, and the stepper motors could not be called whisper quiet by any stretch of the imagination either. What I mean is when it sits idle. Hear it? No, you don't! That's the laptop! There is not a single cooling fan running continuously on this thing. While the power supply does have a fan, it only kicks in after the machine has been running for a while and shuts off again pretty quickly after. So when it's just sitting idle and not being used, the Nova basically makes zero noise. Being used to like 3 of these cursed 40mm jet engine fans in my 3D printer screaming as soon as I just turn on the power, and an even smaller, albeit thankfully single one on the 3018. This feels nothing short of a welcome respite. The loudest thing in the room right now, aside from me talking, is the laptop. And I absolutely love that. Sadly, just when you thought we could finally have nice things, we're moving on to the cons, and this is unfortunately where I have some bad news. The Lunyee 3020 Nova has an incredibly stupid design flaw. Yes, that is quite an allegation, which is why I first wanted to see whether it actually had any practical consequences before immediately tearing into an otherwise promising product. But of course I'm now second guessing that choice due to how it could inherently make me come across as biased. In any case, I don't know about you, but this does not look right to me. Yes, that is a massive amount of backlash in the x-axis, and it's not slapping the ball screw or the linear rails like you might expect, because like I mentioned earlier, those are decent quality with basically no backlash I can feel. No, it's the whole ball screw that shifts. Tragically, the way the machine was designed, that can just randomly happen because there's no thrust bearings to take those forces. On the left, the machine down portion of the ball screw slides into a ball bearing recessed in the frame, which is very good because that'll take any cutting forces pushing the spindle and by extension the ball screw to the left. But the other side is simply attached to the stepper motor shaft via a rigid coupler. Now, if you've ever seen a stepper motor disassemble, you might have noticed that its rear bearing is preloaded by a wave spring washer in the end cap. This means if you push on the shaft hard enough, you'll be able to compress this washer and force the shaft deeper into the motor by like 0.5 millimeter. How much force that takes depends obviously a lot on the stiffness of the spring washer and the amount of preload in the design, but also on the exact tolerances they achieved when machining that specific stepper motor's end caps, making the bearings have a tighter or looser fit, as well as a multitude of other factors like surface roughness and material corrosion affecting friction of the ball bearing in its recess, to name a few. Long story slightly shorter, when I push the spindle to the right, it simply rams the shaft right into the stepper motor because that little wave spring washer is all that's there to take the load. You can even see this when I point the camera at the motor's butthole. So that's the reason we saw the spindle visibly shift to the right in my steel milling test, because it's a very intermittent fault that only rears its ugly head at higher cutting forces. And not only that, it also depends on the individual stepper motor you get on each axis of your machine, because even though it's designed the exact same way, my y-axis here has it to a much lesser degree. I still get some give if I push on the ball screw hard enough, but it takes significantly more force. Again, different stepper motor, different tolerances, different friction. I just happen to have gotten a pretty sloppy motor on X. The ramifications here are pretty insidious because when cutting any materials that don't require particularly high cutting forces, like wood and or working at conservative depths of cut, you basically won't even notice anything's off at first. It's only the plexiglass and the PLA where I can see visible effects on the results. The acrylic gear had this visible step between the first and second pass in some places, and I think I misinterpreted that earlier because I can't actually see the workpiece shift in the footage. So that leads me to believe it was instead this backlash in the x-axis causing it, which makes sense seeing as the acrylic was surprisingly hard and I didn't take a light cut. And even though the PLA ultimately failed and turned out pretty terrible, looking at it, there's actually a big misalignment between the two passes that can only be explained as something other than the workpiece shifting because I had it screwed down. But wait, that's not all, because even though I never got around to testing the accuracy of this machine by milling some tolerance tests, I can already tell even from measuring the center bore of these gears that it would have completely flunked, as most of these holes turn out to be oval, with one direction significantly undersized compared to the other. Again, the spindle might just have shifted ever so slightly. Ironically, this is not the case with the aluminum gear, where I was taking very shallow passes out of fear I might screw up, so cutting forces were accordingly low, and of the entire batch, it is actually the only gear at all to pass Lunyee's proclaimed accuracy of plus minus 0.05 millimeters. This also hints toward a dynamic mechanical issue rather than a badly tuned steps per millimeter setting. As devastating as this is for a machine literally meant to handle higher forces from cutting non-ferrous metals, I'm sure it's an honest mistake. And an easy enough one to make, no less, if the person who designed it did not know about this obscure property of stepper motors. Especially because for 3D printers, nobody gives a hoot. We literally all rely on the stepper motor shafts taking the entire weight of the bed. Not to mention, exact same issue with this 3018 as well. Except here, it won't ever become a problem because it's not powerful enough. The difference is really one of scale. So I'm not going to hold this against Lunyee as long as they fix it. But of course, criticism without a solution is merely an inflation of the critic's ego, so let me demonstrate how you, the customer having already bought, or maybe planning to buy this CNC soon, and Lunyee in their next manufacturing run can fix it, because thankfully, it shouldn't even be that difficult. This knob for manual adjustments at the end of the ball screw is just held on by a little grub screw. All you need to do is get an 8mm ID thrust bearing and put it on there before reinstalling the knob while applying some force as manual preload. And that's it. Now any cutting forces pushing the spindle to the right will also be transmitted into the frame via that thrust bearing. Ideally, you'd also add a Belleville washer or a very stiff spring washer to help maintain the preload and to absorb any minor misalignments caused by the knob not running entirely true, but I forgot to buy any, so this will have to do for now. And to be fair, I cannot feel any backlash between the two bearings, so it might just be perfectly fine. But yeah, that is literally it. Same thing applies to the y-axis obviously, but for the z-axis, which theoretically suffers from the same problem, I unfortunately don't have an easy fix like that yet, because the knob is mounted on top of the stepper motor instead of at the opposite end of the ball screw. However, it also shouldn't be as much of an issue here because the z-axis cannot handle loads that big anyway without the frame of the machine flexing. Okay, so how can the manufacturer fix this? Basically, we're just going to integrate what I just did for the DIY solution into the frame. Lunyee, watch closely. You already have a ball bearing recessed on this side of the plate. All you need to do is counterbore this hole from the other side as well and put a second bearing. Add a stiff enough spring washer, emphasis on stiff enough because we know what happens when it's not, and screw on the knob with a bit of preload. That's it. The cheap and crappy solution. Crappy because vibrations might make this knob come loose after a while. But if for some reason coaxial alignment of these two counterbores turns out to be an issue, just put a big hole all the way through and use flange bearings instead. A nicer solution would be to use two thrust bearings instead of those radial ones, which are not meant to take axial loads anyway, and screw this knob onto the end of the ball screw for much more accurate and reliable preload before tightening the grub screw, keeping it from undoing itself. But that's a bit more invasive of a solution since it requires threading the ball screw end and the knob. But yeah, that is the biggest flaw I found in the 3020 Nova, and if it wasn't so stupidly easy to fix, I would have had to give a big thumbs down because without this little mod, the machine can never be used to its full potential. And in my case here with the particularly sloppy X-axis motor, it sure looks like I would have never gotten accurate results. Now, all my other criticisms thankfully pale by comparison to this design blunder, but obviously the bed is pretty warped from the extrusion pieces being joined together in the middle, so I'd really like to see that fixed too. Not sure exactly what went wrong there without taking it apart, but design-wise it looks good to me. There's no reason it should come out with a kink like that. Next up, of course, the frustrating impossibility of increasing the needlessly conservative default speed and acceleration settings without homing completely braking. I already mentioned my theory about the z-axis end stops there, but to be honest, I haven't had time to properly research it, so maybe take it with a grain of salt. At any rate, having to turn down settings that much for teamwork at all makes zero sense. Like, why would you limit the Z-axis to 100 millimeters per minute if it can do 5,000 like the others? You can ship it with those settings if you like, so newbies don't immediately crash it or whatever, but experienced and impatient users should have the option of cranking it up to unlock the full potential of the hardware they got. Related to that, I found that the claimed maximum speed of 5,000 millimeters per minute is actually a little over optimistic with the stock motor current settings it ships with. I had to turn down my maximum speed to 4,500 because occasionally it would stall on travel moves. This actually ruined the test piece I was cutting for the base of the LED ornament, although I just realized this suspiciously has so far also only ever happened on the X-axis, so it is very possible my X-axis motor is just a lemon. Whatever is the cause though, it can likely be fixed by just cranking up the motor current potentiometers on the controller PCB, but that's a story for another day. And that's about it. For some minor nitpicks, I have the missing protection for the Y-axis rails. I'd have liked to see a sheet metal piece covering those up since they're awfully exposed to any flying chips unless your dust collection is literally perfect, but those are easy enough to 3D print, and you could use a CNC to make them out of wood, plastic, or aluminum as well. I also find the power cord of the trim router to be a bit short. As you can see, I had to make up an extension here because it didn't quite reach the power strip underneath the table, even though the one for the machine itself did just fine. It would be nice if they were the same length. Speaking of cables, the USB connector on this machine is a bit inconveniently placed. Lunyee supplies a cable with a 90-degree plug to get around this, but with a computer right next to it, I obviously didn't need one that long, so I just jammed a straight one in there, and it just barely fits at a bit of an angle like that. However, that's also easy enough to fix ourselves. You just need to make some thick shims to space the controller box like a 1/4 inch from the frame. Last but not least, some general observations. Overall, the 3020 Nova has been really fun to use. Compared to 3D printing, the CNC workflow is still best described as cumbersome, but the capabilities of this machine in terms of rigidity and especially material removal speed actually make me want to use it. I used it a little off camera to cut out this disc for the makeshift turntable I filmed the LED ornament on, as well as the fixture I needed to machine the base in the first place, and being able to quickly sketch up simple shapes in CAD and immediately have them cut out more accurately than I could using traditional power tools feels pretty novel. Of course, I'm comparing my experience to this pile of junk, which totally is not fair, but if I have to spend ages setting up workpieces and babysitting the machine, not least to manually change tools, I at least want the machining process itself to be reasonably fast. So while I might be spoiled now, for me personally, I have to say anything less rigid and powerful than the Nova isn't worth bothering with and might be off-putting more than anything. The Nova costs about 3 times as much as one of those, but it is easily more than 30 times as capable. Now, it is worth mentioning that due to the nature of open gantry machines like this, you're basically forced to run it with dust collection for all but engraving jobs. I didn't because it would have gotten in the way of filming and I don't have a dust shoe yet, but let me tell you, it makes an insane amount of mess. And not only that, the chips and dust get on the rails regardless of my printed Y-axis rail covers, as well as on the X-axis, which is still entirely out in the open. I guess it depends on how much you trust the wiper seals to prevent aluminum swarf and wood dust from ruining your linear bearings, but you're in for quite a project if you wanted to design some rail covers or bellows to fully enclose all axes. Yes, that does sound inconvenient, but as far as I can tell, your options for getting an enclosed CNC in this price range are basically non-existent, save for the SainSmart Cubico, which is not only tiny, but also otherwise incomparable because mechanically it's just a pimped up version of the traditional 3018. if you really want a fully enclosed machine, it seems you'll either have to settle for that, or shell out $2.5 grand for a Carrera Air, or build your own enclosure for the 3020 Nova. And personally, I like the last option here the best. I'd much rather have a solid machine without bells and whistles that does what it's supposed to do well, and then spend some time adding an enclosure and stuff myself, than a big piece of plastic junk full of convenience features and screens that doesn't actually work well and isn't as easy to tinker on. As for other options, the closest match I can find in terms of raw specs is this 3030 from Saint Smart, and while they did put more effort into protecting the rails from dust, it also costs over $100 more, and from the pictures I cannot tell whether they avoided that mistake of ball screw under constrainment. Everything else in this price range seems to trade rigidity for work area and fancy screens. So, should you buy the Lunyee 3020 Nova? Well, I obviously haven't finished my milling test yet, and once I tear the machine down, we'll likely find a few more suboptimal compromises in the design, as is sadly par for the course with products when you evaluate them from a purely technical standpoint. But given my videos take so long, there might be entirely new machines on the market by the time I finish this review series, so realistically, you'll probably have to decide based on what I was able to show in this first video today. Either way, based on what I currently know about the 3020 Nova, I would say if you value rigidity and raw power over a large work area and fancy screens, and you don't mind first fixing it by doing this little thrust bearing mod, which will likely be needed to get properly accurate results without having to go super slow, and is definitely required for any type of machining inducing higher cutting forces, then yes, you should buy it. It's not a perfect machine by any means, but I feel like it mostly comes from the right place, and honestly, I still like it. But ultimately, I can only speak for myself, and your standards might be higher than mine. Big thanks to Lunyee for sending this machine over for a review, and for their patience waiting for me to make a feature film length video about it. It does take some guts to send me a CNC after how critical I previously was of the little 3018, so to have me only slightly annoyed about some speed settings and a missing bearing is a good outcome. Special thank you also to patrons of the channel. I already make few reviews because that's just not what my channel is about, but without their support, I'd be ironically very disincentivized to make any reviews at all because they're just very stressful and a huge time sink, making me lose out on sponsor deals. So it's always funny when companies send emails like, "We've got a special opportunity for you. You get a free machine in exchange for a review video." And I'm like, yeah, you know what? I don't care about your machine. Why would I waste my time making a video on it? All I want is a free product placement. The internet's full of dodgy deals like that. Anyway, I hope you enjoyed. Congratulations if you made it through the entire video, and thanks so much for watching. Bye bye!